Alrighty. So, chapter 9 was about electrons, electron configurations, understanding that there are different areas within the atom that those electrons fit, and there are certain stable arrangements of electrons that make atoms stable, that they sort of gravitate to, that they want to have. Okay? We are going to, in this chapter, use dots to show those valence electrons. So let's have a look at a periodic table. If all you need to do is spot the valence electrons just from their position in the periodic table, it's actually pretty simple, because all we need to do is look at the A group numbers. Okay? We're not really going to do valence electrons in the transition, but in the main group, on the left and the right, those valence electrons are just the A group number. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Probably not 8 for helium. Helium just has 2 because it's that first shell, but 8 for everything else. And those valence electrons are important to us because they're in the outermost shell. They're in the area that's sort of furthest from the nucleus. And they're the ones that are responsible for chemical properties, for reactions, for bonding, for pretty much anything important about an atom. Okay? It comes from those valence electrons. So that's what we're going to be talking most about today. So you'll very commonly have your periodic table numbered 1 through 8 across the main group, because that's how many valence electrons any of those elements would have. So a electron dot structure, or a Lewis structure, will show those valence electrons as dots. Okay? So magnesium. How many valence electrons does magnesium? 2. Yep, it's in group 2. Okay? So let's just draw 2 dots there. Some places will tell you have to draw the dots in a certain side or something like that. I'm not concerned about that. Okay? I just 2 dots. Okay? Chlorine. How many valence electrons? 7. It's over here. Yep. Chlorine, 7 valence electrons. I'll use a different color here, but 5, 6, 7. We'll do that. Okay? So what these are right now are neutral atoms. And we talked about neutral atoms a while back in chapter 4. It's neutral because it has the same number of what and what total? Yeah, the pluses and the minuses, the protons in the nucleus and the electrons around the outside. Okay? Now, we're not showing all of the electrons, we're just showing the valence electrons, the important ones. Okay? But these are neutral atoms. If we counted up the total number of protons and the total number of electrons, they'd be equal within each of those atoms. Okay? So these are neutral atoms, but just because something is neutral, that does not mean it's stable. Okay? In fact, many neutral atoms are very reactive because they would like to lose or gain electrons to become similar to a noble gas. And that all has to do with valence electrons. So what would magnesium like to do in order to become stable? And you can sort of tell from its little structure there, but it's the same answer we would have had before. What would magnesium like to do? Louder? What? Gain? It's going to lose. Okay? In fact, all metals will lose electrons. How many will magnesium lose? Yeah, and there they are right there. It has 2 valence electrons that it would not really like to have. Okay? So its outer level has 2 extra electrons in it. If we got rid of those 2, then the next level down would be full. See how that works? So we would really like to lose those 2 electrons, what would chlorine like to do? Gain how many? 1. What is the sort of magic stable number of valence electrons? 8. Okay. Chlorine has 7. It would like 8, so it's 1 short of a full shell of valence electrons. Okay. So these are going to help each other out. Let's take one of these, transfer it over to that chlorine there. That'll give us a chlorine. That now has 8 valence electrons. And now what charge does that have? Because we gave it another electron. Yeah, that's a minus charge. Okay. This now has 8 valence electrons, which makes it stable. If we wrote out electron configurations, this would end with 3s2, 3p5. Now that we have added 1 electron, it would end with 3s2, 3p6. Those are the valence electrons. That get you 6 electrons through that p block over to the noble gas type configurations. Okay? But that's what makes it stable. If it has that, if it has 8 valence electrons, that means the s subshell is full. That means the p subshell is full, and everything is balanced out and symmetrical, and everything is the way it would like to be. Okay? So where's this other electron going to go? It's not just going to fly away. An electron is never lost unless there's something to accept it. Let's put it that way. And magnesium has to get rid of 2 electrons. So what do you think? How about another chlorine atom? Just because I drew it doesn't mean that's the only thing present in the world, right? If we have another chlorine atom, here, I'll just put it on this side just to make the drawing a little nicer. How about right there? So then, what we'll end up with, the chlorine, right? That's down here. This is now a chloride anion that's stable. We'll have a magnesium. I could draw no dots, okay? Because we sort of got rid of those. What charge would it have? Because it got rid of, it'd be 2 plus. Okay? I could draw no dots, or I could also draw 8 dots. Why would it also be correct to draw 8 dots around that magnesium? Yeah, we've emptied out this shell. Now the valence shell becomes the previous one. Okay? So, but we'll usually just draw no dots if we got rid of those. Okay? And then we'll have that other chloride. That looks like this. A minus charge. 1 more electron that it got. Okay. So this right here, what do you suppose the formula is for magnesium chloride? It's not just MgCl. MgCl2, because we need that 1:2 ratio in order to transfer all the electrons. So that's the real reason. You know, before we were talking about getting the charges to balance out. Really what's happening is that if magnesium wants to lose 2 electrons, and if each chlorine needs to gain 1 electron, We need to have the right number of atoms for those exchanges to take place. Okay? In each case, though, the reason that we did it was to make a stable number of valence electrons. Okay? So in the case of the chlorines, filling out their shells to get them 8. In the case of the metal, magnesium, getting rid of the extra valence electrons so that now the previous shell is the one that has 8. Okay? So that's the general format, I suppose, for what happens when an ionic compound is formed. And ionic bonding, then, is that attraction between these oppositely charged ions. If we have a chloride with its minus charge, a magnesium with its 2+, and another chloride with its minus, there is an attractive force between oppositely charged particles that makes them stick together. Okay? That is the ionic bonding that's happening right in between those oppositely charged ions. So it's a two-step process. The electrons transfer to make them stable, okay, but that gives them a charge. And those charges are what cause the opposite ions to stick together. Does that make sense? Oh, here we go. Bond, ionic bond, taken, not shared. What do you suppose we're talking about when we say taken? Yeah, okay. Electrons were transferred. Oops. And I'll try to remind you of that several times throughout this chapter. But in an ionic compound, when we've got a metal and a nonmetal, the electrons were transferred from one to another. Literally, one of the atoms took the electrons. So if you think of the chlorine up here, really what this chlorine does, it takes that electron away from magnesium. Magnesium doesn't want it. Chlorine really wants it. So there's a transfer that happens here. Okay? We'll have a little bit more talking about ionic compounds coming up later. Oh, what I do want to remind you of, way back in chapter 5, I showed you this picture of ionic compounds. Okay? That three-dimensional lattice of opposite ions. When we have a pure ionic compound, it's all the opposite ions stacked up, alternating. And the reason it's like that is because any one ion is attracted to opposite ions sort of on all sides. So it's important to remember that it's not only this that makes an ionic compound. Here, let's actually write that, the ionic lattice. Stacks of alternating ions to make an ionic solid. Okay. So any one ion will be attracted to any other ion of the opposite charge. So they'll sort of self-assemble, stacking, alternating like that in order to have a stable solid. Okay? Does that make sense? But it's really important that we have that little picture in our head, because when we talk about molecular substances, the picture is entirely different. We need to make sure that ionic and molecular that we fully appreciate and understand the difference between those. Okay?